Yes. Okay. Um, Today I want to talk about, should I call it molecular orbital theory? But when I write that, it seems too chemical. So in particular, I'm going to talk about linear combination of atomic orbitals. So we are going to try solving the electronic structure of actual materials, starting from their atomic counterparts. So let me just draw you. This is a hydrogen, let's say. Okay. There is a nucleus, and the electron revolves around it, and we can write a Schrödinger equation for it. It has a Hamiltonian. That Hamiltonian basically describes how this electron interacts with that nucleus. Okay? We have solved this in a computer, and we got ourselves these orbitals, right? Do you remember that? At least in the computer we have seen them. Now imagine you have another one of these nuclei, and they are far away from each other. So for this one, you also have H0 phi 2 equals E0 phi 2. The H0 and phi 2, E0, the E0s are the same because these nuclei are the same. Okay. However, there is phi 1 and phi 2 because phi 1 is a function centered here. So let me just write it. Phi 1 is centered here. Phi 2 is centered here. But in general, it's the same function, just shifted, right? Now, what happens when you bring these atoms together? These atoms have atomic energy levels, right? Let's say this is the ground state. This is the ground state energy level. But when they come together, they split. These energies split, right? They split into bonding and antibonding, to use that chemical language now. And we will see how this happens in this course, okay? In this hour, hopefully. Okay. Let me erase this because we have already drawn this over here as well. Now, how do we approach this problem? We think about their interaction with each other. So let's bring these nuclei close by. Okay. Then this is H0. This interaction is H0. But there is an H prime that is due to this one seeing that one. Because of that, you have H prime. Do you agree with this? Yes? And similarly, there is an H0 for this orbital, but it does see the other nuclei, It does see the other nuclei. Does it make sense? So there is H0 that determines the orbital when they are far away from each other. And then there is H prime, which comes from interaction. Okay? So what we are doing here is approximation. We are trying to solve this by an approximation. and the approximation, how we do it is summarized in its name, linear combination of atomic orbitals, right? So I have an orbital phi 1 here, and I have an orbital phi 2 here, and I claim that phi is some coefficient times phi 1 plus b times some plus some coefficient times phi 2. So I use these two functions, I sum them together in a certain ratio to get one function out of that. And I'm hoping that if I solve h0 plus h prime times phi equals to E phi, I will get my energies. So these will be energies of the molecule, while these were energies of atoms. Let me write individual atoms. So far, how are we doing? Are you following? There is a bit of mathematics here, but it's doable. Don't worry. Okay, you've got this. So what are we dealing with here? We have phi 1 that is concentrated on one side of, and phi 2 that is concentrated on the other side. Oops. Okay. So we will have some assumptions. Let me start with those assumptions. First assumption, you already know this. Phi 1 star phi 1 over the volume is equal to phi 2 star phi 2 over the volume integral. And what do you think this is? Anyone? Anyone? 1, yes. Yes, it's 1 because of normalization. Okay? The reason for this one is normalization. Okay, then there is something that we will just give a value to it. Phi 1 star h prime phi 2 dv equals to phi 2 star, simply because of symmetry, this is the case, and this is minus t. Okay, there is some value that comes out of this integral, and it's negative usually, and this will define the interaction. Do you see how it defines the interaction? Say it again. Well, we are actually going to set the overlap of two orbitals to 0. We will assume that that's the case. This is more of hopping integral. This is called hopping integral. Physicists think of this as it basically defines you the probability of electron hopping from this one to the other one. Okay. Okay, it's a measure of interaction, and we will just give it a number, and we will deal with it with a number. It is important though. Then there are assumptions, two assumptions for simplicity. Okay, first assumption is integral of phi 1 star phi 2 dv it's not because of orthonormality, it's simply because of we are assuming that this is negligible. Okay? So orbital overlap is going to be set to 0. 0 orbital overlap assumed. All right. What else? Final assumption. Thanks for your patience. Phi 1 star H prime phi 1 star is equal to phi 2 star H prime phi 2 star. No. Yeah, this is better. Will be assumed to be 0. This is also an assumption. Okay? Very good. DVs are here. So let's now go back to where we started. We started with this formula over here, right? So let's plug this one inside and see where it goes. So let me just, so it says that H0, sorry, let me change, yes, H0 plus H prime multiplied by A phi 1 plus B phi 2 is equal to E times A phi 1 plus B phi 2. That's our main equation. And then based on these assumptions, we are going to get some nice results. Okay? Do you have any questions at this point? Very good question. Second assumption means, so you are basically taking phi 1. Okay, let me gather my thoughts. So if it's phi 1 H0 phi 1, then it's like expected, it will give you energy, right? It will give you E0 because, okay, let me not write with disappearing ink. H0 phi 0 is E phi 0, right? So if you write integral phi 0 star, I shouldn't write phi 0, phi 1. If I write phi 1 star H0 phi 1, then what do I get? E0. Did I already write that? Okay, I didn't write that because I didn't need to write that, but this is the case. Do you agree with this? Yes? Why? Because that H0 is directly interacting with, so it's basically this orbital and Hamiltonian due to that particular nucleus. Okay? But when I do phi 1 H prime, then it's like taking phi 1 times something that is far away times phi 1. So you get something very small. Do you buy this argument? Sort of, right? The point is that we are going to get something very simple at the end, and I don't want you to have the illusion that it is always the case. There are lots of assumptions that we are making to bring it down to that simplicity. So it's not the truth. Okay? Good. So actually, since I just showed you that, I'm tempted to do something. Let me not do that. Let me just go ahead and just open it up. H0 times A phi 1 plus B phi 2 plus H prime times A phi 1 plus B phi 2 is equal to the same thing. E A phi 1 plus B phi 2. Now, what is H0 phi 1? E0 phi 1, right? So the operator becomes a number. So E0, and the same is true for phi 2, right? So I can write it down like this. Nothing that simple is happening with the other parts. So let me just copy those parts and duplicate it and put it here. Okay, good. So can I just take this to the other side and write it down like so? E0 minus E times A phi 1 plus B phi 2 plus H prime A phi 1 plus B phi 2 is equal to 0. Okay, we are not done yet. To simplify things, I can take the integral of this equation. So I take this equation and I take the integral of phi 2 star dv integral. What do I get? So phi 2 star phi 1, what do I get from here? 0. What do I get from here? 1. This is a hard one. What do I get from this one? Minus t. Very good. Very good. And what do I get from? Yes, you get 0 because of the assumption. Do you remember when it's phi 2, h prime phi 2, what you asked gives 0, right? So this integral brings me the equation that can be written like this. B times E0 minus E minus AT is equal to 0. Do you agree? Do you see how simple it is now? But there are two variables, so we need another equation. The other equation is this one. So what happens with this one? When I write phi 1, so what do you get from here? 1. From here? 0. Here? 0. Minus t. Everyone agrees? Yes? So I get another equation. A E0 minus E minus bt equals 0. Yes? Good? Amy? So I can write this as a matrix equation, right? Look at this. E0 minus E and then minus t, E0 minus E, AB equals 0. Or to put it in a more Hamiltonian-like thing, basically you get a Schrödinger-like equation in terms of the coefficients. So let's remind ourselves how we started. We started by saying that my molecular orbital is a linear combination of my atomic orbitals, right? Then it turned into this kind of an equation. So let me simplify this for you even further. to understand how this works. So I have two atoms, atom number 1 and atom number 2. Okay? Hello. To construct this matrix over here, you basically what this is called? On-site energy. Okay, it's called on-site energy. So what is the energy of that site when it's isolated? Yes? So that is E0. So I write into 1 by 1 E0. Are you following? Then 2 by 2 is also E0. What is the interaction 1, 2 minus T? I write it minus T here. What is the interaction 2, 1? Also minus T. I write minus T here. That's basically how you get this matrix. Okay? So now you know how to apply tight binding or linear combination of atomic orbitals. T is representing the interaction. How strong is the interaction between those two atoms? Okay? Yeah, it's hopping integral. Yes. Very good. So let me just, if you have, let's just make a small homework here. 1, 2, there are no homeworks, don't worry. You already got the last homework. But if you have 3 atoms, how would you write tight binding for these 3 atoms? First of all, what is the size of the matrix? 3 by 3, right? So you have on-site energies E0, E0, E0 on the diagonals, right? You have interaction between 1 and 2. No interaction with 1 and 3. And we have an assumption there, by the way. It's called nearest neighbor tight binding. So you might also have next nearest neighbor tight binding, in which case you also have interaction with 1 and 3, which sometimes is needed to explain stuff. So this is the matrix that you need to solve to figure out the energy spectrum of this system. All right. Yeah. Also, E0s can be different. What if you don't have all carbons but boron and nitrogen? Then each one has their own E0s by themselves. Plus, there could be multiple orbitals in one site. So right now, what we are doing is we are assuming that there is only one orbital, like let's say we are solving s orbitals. But what if you include also p orbitals? Then you have complications, okay? Then your matrix, for example, becomes 6 by 6. So it's number of orbitals versus the number of orbitals. All right. So what? So let's solve this simple case. Which is this one, right? E0 minus T E0 AB E AB. It's an eigenvalue equation. How do you solve it? E0 minus E squared minus T squared equals 0. Do you agree? Yes or no? So E0 minus E is equal to plus minus T, which tells you that E0 is either E is either E0 plus T or E0 minus T. Did you follow everything so far? So based on the interaction, as you bring them closer and closer and closer, T parameter increases, the interaction increases, and there is a splitting between the orbitals, right? There is a bonding and antibonding, and we will see that why one of them is bonding coming soon. How do you find the eigenvector for each one of them? So there is lambda 1, or let me call it E1. Will it confuse you if I say E1? It will, right? You will think that it's the first atom's energy. So the eigenvalue, one of the eigenvalues is E0 plus T. So how do I find eigenvector? What do I do? E0 minus lambda minus T, E0 minus lambda 1. This times AB should be 0, right? So what do I get from E0 minus lambda 1? Minus T, right? Everybody agrees? So I get minus T, so which means that I have basically the matrix minus T, minus T, minus T, minus T, AB equals 0. This tells you that the first eigenvector is 1 minus 1 with 1 over square root 2. Do you agree? Everyone? Yes? So, your first solution, E0 plus T energy corresponds to 1 over square root 2 phi 1 minus phi 2. That's the solution, right? Because A and B were coefficients. How about lambda 2? When energy is lowered, then E0 minus lambda 2 is T. Then you have T minus T minus TT, AB. Then the vector is 1 over square root 2, 1, 1, right? Which tells you that for E0 minus T, the solution is the sum of orbitals. Yes? Then we can draw a nice diagram of this. So these atoms by themselves, they had some wave functions like this, and this one is like that. But when they come together, there is a lowering in the energy. So this is E0, this is E0, this is E0 minus T. When these two individual orbitals come together, they create two molecular orbitals. One of them is this one, duplicate, put it here, duplicate, put it here. This one plus that one, so this one has a plus sign in between. So in total, there is an accumulation of density in the middle part, which we call bonding. Right? That's what we talk about when we say that two carbon atoms making covalent bond are sharing same electrons. What we are talking about is they are combining their orbitals to form a bond, and that lowers the energy. Okay? Bless you. While the antibonding has higher energy, right? Antibonding, I should have written it down. So then this time I have again these two things, but I'm basically summing the negative side of the other one. So it's like this. So there is a depletion in the mid part. That's why the antibonding orbitals look separated, right? Are you with me? And they have higher energy. Doesn't mean that they are not going to be filled. It depends on how many atoms you have, how many electrons you have, etc. Do you have any questions, comments, ideas, suggestions? No? Should I move to the next part? This is perfectly clear? No, good. So what we have seen is how to deal with electronic structure of molecules, right? And this is the simplest idea that I can tell you. But what if you have 10 to the 23 atoms? How you deal with that? Sometimes it's easier to deal with 10 to the 23 atoms than with 5 atoms. Okay? Believe it or not. Especially if those 10 to the 23 atoms are arranged in a crystal. So what do I mean by a crystal? Let me draw you a monoatomic crystal. Atomic chain crystal. So I have nuclei arranged like this, and it goes on forever. Okay? What does it mean? It means that the electron is seeing a periodic potential. It's seeing a periodic potential, and it goes on forever. That's why it's easier to deal with forever than with finite, because if it's just this much and that's it, then we have 1, 2, 3, 4, 5, 6, 7, 8, 9 atoms. We have to build a 9 by 9 matrix, etc. Okay? But if we assume that it continues forever, then we can concentrate on solving only this part, and it will just be repeated on the other sides. But it's not just that easy, okay? By the way, this is monoatomic crystal. I can have a diatomic crystal as well. Let me show you diatomic crystal. Could be something like one atom, then the other atom, and then repeated. This is like a one-dimensional salt, right? So in this case, you cannot simply solve the problem by doing this, because there's another atom there breaking the symmetry. So you need to deal with this one, right? And that's what we call a unit cell of a crystal. Now, let's say you have a crystal and you want to solve the electronic problem. I will just jump straight to the answer here and not rationalize it. It turns out that when you have a crystal, you have a special condition. It's called Bloch's theorem. Have you heard of this? No, right? Bloch theorem tells you how to solve electronic problem in periodic potential. Periodic potential. Okay? Just like here, there is a periodic potential. It keeps repeating. The same thing keeps repeating. Bloch tells you that in these cases, the solution must be in this form. The solution must have a repeating part and multiplied by a plane wave, where u of x plus a is u of x. You might be thinking naively from, let's say, mechanical engineering that I can just simply put a von Neumann boundary condition here, right? Whatever the electronic problem is going to be, just make sure that the derivative at the boundaries is 0, so that it just connects to the other side nicely. Does it make sense or not? It makes sense to you. Okay, good. But this is not the case with the electronic problem, okay? The wave function, the total wave function, is composed of two parts. So, one part of this is a periodic potential, so it could be periodic solution, something like this maybe. Periodic part. This is the ux part. And then it's multiplied by a plane wave, which doesn't need to fit into these things. Okay? Doesn't need to fit into that. It just has its own wave vector. Okay? Now multiply these two. So this is e to the ikx, and k can be anything, but we will see that the subset of that anything actually defines everything else. We will come to that. But it can be, in principle, anything. So, what do you get when you multiply these two? So you can let's just look at the values that we have right when they are at the top. Okay? So I have some small amount here, and then a small amount here, but then it becomes negative, then it becomes negative, then it becomes positive, then it becomes a bit more positive. Do you agree? So I've multiplied the red curve with the green curve to get the blue curve. Yes or no? Let me make it more clear. Let me make the green curve much more regular, like this, okay? The red curve is like this. So what do you get? You get something like this. When you multiply them, you get this is multiplication, not a summation. It looks like I have summed them, but I was trying to multiply them. Does it make sense? Yes? So that's how you get this. It could be, let's say, it could be pi z orbitals, could be carbon chain, and each carbon has its own pi x and pi y that looks like this, like pi x and pi y. So it's very hard to draw, so I will not. I was going to draw one side green, one side yellow, but do you have time for that? Like if I draw something like that, let me just use technology. So I have something like this. This is a pi orbital, right? Plus and minus. And then I will duplicate it many times. Duplicate, 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 duplicate. Let me even put them closer so that you see the contrast. Okay, I can also do this. So this would be your U. This is the U. Then it's multiplied by e to the ikx, right? Then you have here, unfortunately, copying will not work. So up, a bit more up, a bit more up, a bit up. But then okay, is it already down? I think it's already down. You get the idea, right? So it goes like this. Good? So that's how it looks like. And what is this k representing? This k is representing, so that k is the wave number, and h bar k is something we call crystal momentum. So the electronic structure would appear to have this crystal momentum. It would interact with whatever you are sending to the material. It would interact with the electronic structure as if the electrons inside that material have that energies and momenta. Okay. So I think we magically have time to deal with the next thing as well. Or should I stop here? You want to stop here? Okay. What we are going to do next time is, we have learned how to deal with two atoms, right? Now we will do it with infinite atoms, and we will apply Bloch's condition and see how it changes the tight binding parameters. And we are going to get bands, electronic bands. And hopefully you will understand what is all this conduction and valence band is all about, okay? All right, let's stop here.